Hello everyone. This video I'm going to talk about the 2D kinematics or 2D and 3D kinematics, but mostly 2D. Most of times 2D. Okay. So and in last video we introduced the vector. Okay, and we say if you want to do the vector calculation, if you only use the graphically in representation, that will I sometimes cannot handle difficult problems, so we need another representation of a vector, and it's called component representation. Okay, so when we use the component representation for a vector, and we need to set up the coordinate. And the coordinate, in order to set a coordinate, we have to introduce a concept called unit vectors. Okay, and the unit vectors it's just the vector to represent the direction. Okay, so in the unit vector, why it's called unit? Okay, that's the first thing. The why it's called unit vectors. Okay, it means its magnitude is all exactly one. Okay, exactly one. That's why it's called unit vectors. Okay, its length is always one, and it's describing the direction. And in conventional notation, I is for x, I and with a head. For unit vector, we always give it a head. Okay, this is called head. Okay, it's this symbol is called head. I head, j head, and k head. That's the conventional unit vectors. And I hat means x direction, j hat means y direction, k hat means the z direction. That's a conventionally we use. And it's a right-hand coordinate system. So that means if you right-hand coordinate view x, if you right-hand course, yeah, I will explain that. So if this is your x and this is your y, or y, yeah, if this is x direction, this is the y direction, and where the z direction should be, just a right hand root, just do the cross. For example, for x, y, where should the z direction be? Is do the cross. Okay, do the cross. Okay, just do the cross. I'm not sure. Do the cross, and your some direction, that's z direction. Your x is here, y is here, and do the cross. Your thumb direction is z. Okay, that's called right hand coordinate system. Okay, that's unit vectors. Okay, how do we represent the vectors by component? Okay, I think that just you all learn this before, so let's quickly review. So right now, if I have we only have x y direction. Okay, x y direction, only 2 dimension. Okay, let's not make things complicated now. We only have 2 dimension, and here is a vector a. So how do we represent this by vector by component? We just project this vector on these 2 coordinates. Project this vector on this coordinate and x and y direction. Okay, do the projection. So we can represent the a vector by component x. It's x component of a on x direction, and y component of a in the y direction. And what's the number of component? So it's the magnitude of a vector times cosine theta. Okay, what's the theta? Theta is here. Okay, and what's the value of a y component? It shouldn't be here, right here. Okay, what's the value of y component? So it's just the magnitude a times magnitude of a times sine theta. Just easy to understand. It's just a projection. It's just a projection. You just use the trigonometric function. You can easy to understand the sine theta and cosine theta. Okay. And here we need to a new definition. Not new definition. So what's the magnitude of A? Okay, what's the magnitude of A? The magnitude of A exactly is okay. So here, when I use this symbol, okay, this symbol is called magnitude. Magnitude. Okay, it's the same as when you use absolute value. Absolute value you use this bracket, right? Not bracket. It's two bar. It's two vertical bar. Okay, this two vertical bar means sometimes means absolute value, and we use the same symbol to represent the magnitude of a vector. The magnitude of vector is just the square sum of the component, and do the square root. Okay, and do square root. It's very easy to understand. It's just I don't know, like I say, there's a rule in trigonometric. I don't know. I forgot the English name. It's Pythagoras rule. Okay, it shows that the length of this the length the length of this vector is equal to this component square plus this component square, and then do the square root. Okay, so this is a component representation of a vector. Uh, okay, if we know this, so how do we do the vector algebra? That means let us start a very simple example, just the plus and minus, plus, okay, okay. When we want to add the two vector together, we just add component by component. Okay, here is vector A, and vector B, and AY is a component of A, BY is a component of B. Okay, when we add these two vector together, we just add component by component. Okay, the component in x direction, add the component, add the x component of A, add the x component of B. The y component of A, add the y component of B. Add component by component. Okay, here is a very good picture. It shows that previously we used the tailhead using a graphically show the addition of vector, and now we use a component language to represent the addition of vector. Actually, they are equivalent. You can see this picture. It's very beautiful picture to show you the component. The component we just add a component. Component is really is it's the same as the graphically representation of vector. Okay, it's really nice. Okay, just x component, b x component of A, x component of B, y component of A, y component of Y, and the resulting factor. Yeah, it's really nice. Okay, and what's the ten and then what's the theta of the resulting factor? Okay. Oh, sorry. The theta means its angle with respect to the x direction. Okay, it's the theta. Oh, sorry, I was wrong to. Okay, this is theta. Okay, so actually, he just said tangent theta is Rx equal Ry over Rx. Very simple trigonometry. Very simple trigonometry. And we are dealing with this triangle. We are dealing with this triangle. So the tangent theta is Ry over Rx. Okay. And the magnitude of the final resulting vector is x component square plus y component square, and then do a square root. Just the same. Very beautiful. Okay, so And next, okay, if we can represent a vector by component, so what about can we use this in the kinematics? Of course, we can use this in the kinematics because because like we just say in kinematics, displacement is a vector, velocity is a vector, acceleration is a vector. So this component representation also is also valid in 2D and 3D kinematics. Okay, so let me show what should be addressed. Mhm. Okay, okay, let's see. Let's show a little. Let's show a little representation of vector. Okay, so let me do very simple. Should we use this? I should use the clean. Yes, let me use a clean white chart. Well, okay, suppose we have a trajectory function. Suppose we have a trajectory function or the position vector. The position vector. A position vector, let's say it's A. And a position vector will have x component, y component, and z component. Okay. And last time, then the x, y, z is a function of time. It's a function of time. It's it doesn't have it doesn't it doesn't has to be a constant. Okay, it's a called trajectory. It's a position. The position vector x component, y component, z component, and each component could be function of time. And what do you remember? What's the instantaneous velocity? It's dr over dt. Okay, let's do a little calculus. So that's dt. Okay, so what this should be? Z. It's very wrong. Sorry. It should be J. It's easy to make this with IJK. Okay. Okay. So what this would be, we put this in derivation. Okay, and let me show you. The derivative is distributive. Is not. It's valid distribution law. Okay, distribution law is valid in derivative, so it will become xi dt plus dyj dt plus dzk dt. Okay, then and I show here I'm telling you there's also another rule in derivatives called product rule. I write it down. Or write it down. Here is product rule. The product rule in derivative. If I have function, I have two functions times two together, and do a derivative. It becomes the derivative of first function times g and plus f times derivative of do a derivative function on g. Okay, it's called product rule. So we now have a similar situation. We have x and the unit vector I, and doing derivative with respect to t. So after applying the product rule, what we have? We have dx dt I plus x times di dt. And similar thing will happen in the y direction. Yeah, just writing the same thing. Oh, sorry, z dt k plus Z times dk over dt. And so and then we'll show something because in very simple question, the coordinate is independent of time. Coordinate is dependent of time. In simple case. And later of this semester, I think when I talk about rotation, I will show you a little bit. Actually, the coordinate sometimes coordinate is a function of time. Okay, right now because right now we are doing very simple problem, so right now the coordinate system is not a function of time. Okay, but in further in rotation, you cannot take this for granted. In rotational motion, your coordinates are not a function of time. But right now, a simple problem. So coordinate is not a function of time. So that means your coordinate is a function of time. So that's why the coordinate does not change. So that means it's zero. Alright, it's also zero, and it's all zero. Is all zero. So finally, you will left this dx dt I plus dy dt j plus dz dt j dz dt I j k. So we are on this velocity vector. So dx dt is the velocity x component of velocity, and dy dt is y component of velocity, and dz dt is the z component of velocity. Okay, so actually it's tell you can actually this equation tell you can treat the motion independently. Okay, you only have to treat the x direction, y direction, and z direction. If you give you the position vector, you can treat if you get a position vector and then you want to find out the velocity on each direction, you can treat it independently. Okay, dx dt is a velocity x component, dy dt y component, dz dt is z component. You can treat the motion independently and help you to solve the problem. You don't have to put all the problem together. You can deal with component by component. Okay, so similar thing happen in the acceleration vector. Okay, acceleration vector is the doing the derivative of velocity vector with respect to t. So we just do it one more time, but I won't show you the complete result because it's almost the same. Y component j and z component k. Yeah, we just do the similar thing. So finally, you will reach the x component of acceleration is dvx over dt, and the y component is dvy dt, and the z component is dvz over dt. Yeah, you can treat the motion independently. Each coordinate, each component, each direction, and just dealing with each component in each direction. And okay, so that's very good things. That's help you really can reduce the difficulty of problems. Okay, so that's pretty much about the representation of a vector by a component language. And the next video I will show you. Let's just show you. Okay, so we in the 1D kinematics we have the equation of motion, two important equation of motion, and what will the equation of motion looks like when using when using component language, and I will show you in the next video. Okay, this pretty much about this video. Okay, hey, see you next video. Bye bye. Oh, you. Oh, very much about this video. Bye bye.